You are lying in your bed now, the world dimming softly behind your eyelids. You feel the slight pressure of the mattress beneath you, the hush of the air around you, and that subtle sense of slowing. A winding down of thoughts that have moved too quickly for most of the day. There is no hurry now. Time, if you can believe it, is not something to race against tonight. It's something we're going to drift through, together. I want to tell you a story. Not just a story of clocks and calendars, though those too will come into it, but the story of time itself. The kind of story that hums gently in the background of the universe, that ebbs and flows, not just through ticking seconds, but through the pulsing rhythm of galaxies and the soft breath of dreaming minds. A story not of answers, but of questions. Quiet ones. The kind that wrap around you like a warm blanket as the night begins. Time. You say the word and it almost disappears. One syllable. A breath. And yet, for all its simplicity, it is one of the strangest, most persistent mysteries in all of science, and in all of life. Have you ever wondered, what exactly is time? I mean truly wondered, not in the casual calendar kind of way, but in the deep, staring out a window on a rainy day kind of way. You may find, when you do, that there's not an easy answer. Physicists have tried, philosophers have tried, even poets have tried. And the more we ask, the slipperier it becomes. But here's the thing. That slipperiness, that mystery, is where the comfort lives. Because if time is strange, then we don't have to feel so strange inside it. So let us begin. Not at a beginning, but at a place you can imagine. Picture a forest. Not one you've been to before, but one that feels familiar in the way dreams feel familiar. Tall pines, moss-covered ground. The light falls through the trees in shafts, slow golden shafts that don't seem to rush anywhere. You can hear a stream in the distance. There is no path. There is no need for one. You are simply there, breathing in, breathing out. And in this forest, time behaves differently. If you stay still long enough, you notice something odd. The shadows don't stretch. The sun doesn't move. The leaves sway, yes, but not with the wind. Almost as if they sway to a rhythm only they can hear. The moss is thick and cool, and when you run your fingers through it, you feel a softness that stretches the seconds. What if I told you that, in a way, this is closer to the truth of time than the hands on a clock? Because you see, clocks do not measure time as it truly is. They measure time as we want it to be. Regular, predictable, controlled. But nature does not tick. It flows, it pulses, it spirals. And perhaps in this forest, we are beginning to remember that. Now, back to you, there in your bed, in the quiet space between thoughts. Let's talk gently about what we think we know. Physicists define time as a dimension, like space. You can move left or right, up or down, forward or backward. And time, well, it flows in one direction. Forward. From past to present to future. That's what we call the arrow of time. A poetic name, don't you think? But here's a curious thing. Most of the laws of physics, the fundamental rules that describe how particles and planets behave, they don't actually require time to move forward. The equations are reversible, like a video that could be played backwards and still, the math would hold. This symmetry, this time reversal invariance, exists in nearly all our physical laws. Except one. There is one place where time only ever moves forward, a law that creates that arrow. That law is entropy. Entropy is, in simple terms, the measure of disorder. The more chaotic something is, the higher its entropy. And the second law of thermodynamics tells us that, over time, entropy tends to increase. In other words, things fall apart. Ice melts, buildings crumble, stars burn out. And this is why we remember the past, but not the future. This is why the tea cools, but never heats itself back up. Entropy is the heartbeat of time's direction. Not because the universe has to be messy, but because statistically, there are just more ways for it to be disordered than ordered. Imagine a deck of cards. When you open a brand new one, they're arranged perfectly. Ace to king, suit by suit. That's low entropy. But shuffle them even a few times and they become randomized, higher entropy. Could they return to their perfect order? Yes, but it's unlikely. Very unlikely. This is time's secret rhythm, from order to disorder. Now, imagine you are that deck of cards. Your life, your thoughts, your days and nights, they begin tidy, full of promise, but they tumble, shuffle, unfold, and that's okay. Because in that shuffling is your story. It doesn't need to go backward, it just needs to flow. The ancient Greeks had two words for time, chronos and kairos. Chronos is the time of clocks, sequential, measurable, one thing after another. It is the time you chase when you're late for a meeting, or counting the minutes until your oven dings. But kairos is something else. It's qualitative. The time of rightness, the perfect moment. The time when everything feels exactly as it should. And perhaps what you are entering now, as you listen and breathe and drift, is not chronos, but kairos. You see, your body doesn't tell time by the clock on the wall. It tells time by the light in the sky, the food you eat, the temperature around you. Your cells have tiny clocks inside them, circadian clocks, and they talk to each other in a language of rhythm and chemistry. Together, they orchestrate your wakefulness and sleep, your hunger and healing. They are not ticking, they are dancing. Inside your brain is a little bundle of neurons called the suprachiasmatic nucleus. It sits above the place where your optic nerves cross, like a tiny conductor watching the sun's symphony. It takes in light signals from your eyes, processes them, and tells your whole body, it's morning now, or now it is night. But here's the gentle wonder of it. Even if you were locked in total darkness, your body would still keep time. Not perfectly, but closely. Because time is not something outside you. It is something you are made of. Think of your heartbeat. It does not tick, it pulses, it swells and contracts. It is not measuring time, it is making time for you, with you. The science of chronobiology, the study of biological rhythms, shows us how deeply time is woven into the fabric of life. From the opening of flowers at dawn, to the migration of birds, to the timing of cell division in your body, it's all time, but not clock time, not chronos. It is something deeper, something older. In fact, some scientists think that even before there were stars, there were cycles. Long before the Big Bang, before particles even formed, there may have been fluctuations, oscillations, tiny pulses of energy in a quantum field. And from those pulses, rhythm. And from that rhythm, the possibility of time. It's hard to imagine, but close your eyes for a moment and try. Picture the entire universe before it began. Not a black void, because even blackness is something, but a state of nothing. No space, no matter, no time, and in this nothing, a shimmer, a ripple, and that ripple becomes everything. What if that ripple was the first second? You see, time doesn't begin with the Big Bang like a stopwatch. It emerges like a melody from silence. And now, lying here, listening, you are connected to that melody. Every breath you take, every neuron that fires, every flicker of a dream, it is all unfolding in time. But here is the beautiful twist. You do not have to chase it. You do not have to control it. You can feel it, like a current in a slow, warm river. You can close your eyes and float. Let me tell you a small story. Once, a clockmaker lived in a quiet town at the edge of a river. He made no ordinary clocks. His clocks were not precise. They chimed not on the hour, but when the wind blew a certain way. Their hands moved with the seasons, not the seconds. People said they were broken, but But the clockmaker said no, they were honest. Time is not a prison, he said. It is a poem. And he was right, because time is not something that happens to you. It's something that unfolds with you. Tonight you are not trapped in time. You are carried by it. Like a leaf on a slow current, you drift, gently, without needing to steer, without needing to worry, because the universe does not rush. Galaxies spin in patient spirals. Stars take billions of years to die. Even light, the fastest thing there is, takes time to cross a room. There is no hurry. There never was. So, why should you? Let your breath slow now. In, outside, softly. Let the weight of time rest around you like a quilt. You are not late. You are not behind. You are not too early. You are exactly when you are meant to be. And as you drift, know this. Time is not your enemy. It is your companion. It is the quiet rhythm in your chest, the hush in your bones, the gentle turning of the world. And we are just beginning. The mind's clock. You might assume that time is a simple progression of moments, that it moves forward at a steady pace, evenly, predictably, and universally. But it doesn't. Not to your mind, not to your body, and certainly not to your memory. Time is more a function of perception than it is of ticking. It doesn't move independently of you. It bends under your attention. It dilates under fear. It compresses under routine. The question is not just, what is time? But rather, what does your brain do with it? Let's take that apart. Start with this. There is no universal now. You experience a present moment, but that moment is a construction, assembled in your mind from fragments. What you call now is not a razor-thin slice of existence. It's a buffer, a window, about 2 to 3 seconds wide. That's the span in which the brain gathers and integrates sensory information, stitching it together into something that feels immediate. This phenomenon has a name, the specious present. It's not an error or a glitch. It's the brain's solution to a biological problem. Signals from the world don't all arrive at once. Sound is slower than light. Touch travels through nerves. Even the retina sends different parts of an image at different speeds. But somehow, you don't perceive a scrambled world. You perceive coherence. Why? Because your brain is not passively receiving time. It's actively reconstructing it. The philosopher Edmund Husserl described this in the early 20th century, not in scientific terms, but in phenomenological ones. He observed that we do not experience isolated points in time. When you hear a melody, for instance, you don't just hear the current note. You hold the previous notes in your mind while anticipating the next. Time, then, is layered. The present bleeds into the past and future. It has depth. Modern neuroscience confirms this. Functional imaging shows that certain areas of the brain, particularly the prefrontal cortex, are involved in creating a sense of temporal continuity. These regions don't just store events, they forecast, evaluate, and update timelines in real time. And these mechanisms are far from perfect. Memory isn't a recording device. Every time you recall an event, you reconstruct it. Your brain rebuilds the scene, often mixing in fragments from other memories, emotional states, or expectations. The result feels coherent, but it's not reliable. That's not a failure, it's a feature. Your mind prioritizes meaning and narrative over fidelity. This has consequences. One is that your past is not fixed, it's flexible. And because your sense of time is built on memory, your perception of duration, sequence, and significance is also fluid. This is why emotionally charged moments feel longer, and why weeks spent in monotony seem to vanish from memory entirely. Novelty and attention are the key variables. When you're exposed to new information, new environments, unfamiliar tasks, your brain works harder to encode the experience. It lays down more neural patterns. Later, when you recall those moments, they appear stretched in time. Conversely, when your days are repetitive, Your brain consolidates similar experiences into fewer memory traces. In retrospect, those days feel shorter. That's why childhood summers felt endless, and adult months feel disposable. This is not poetic sentimentality, it's biological compression. The hippocampus, the brain's memory center, is sensitive to novelty. fMRI studies show increased activation when subjects encounter new stimuli. Repetition dampens this response. With routine, the hippocampus becomes conservative. It records less. So the equation is simple. More novelty equals more perceived time. Less novelty equals less. This leads to a troubling conclusion. If you want your life to feel longer, you don't need more time. You need more difference in time. Routine shrinks perception. Change stretches it. Now, zoom out slightly. You'll notice another effect. Emotions modulate time perception. In situations of high stress, time dilates. Your heartbeat accelerates. Your senses heighten. Your attention narrows. You process more information per second. Later, the moment seems longer than it was. This has been tested. In one experiment, researchers dropped subjects from a tower into a net and asked them to estimate how long the fall lasted. Subjectively, participants reported longer durations than actual clock time, but their perceptual accuracy didn't improve. They weren't seeing in slow motion. They were just remembering more events per second. Their memory density increased. In other words, intense experiences don't literally change time. They change the resolution of memory, like increasing the frame rate on a camera. And again, the effect is asymmetric. Boredom does the opposite. It slows your internal clock. But retrospectively, those periods vanish. Time seems to crawl while you're experiencing it, but leaves no trace behind. Attention is the mechanism. Directing focus inward slows time. Distraction disperses it. That brings us to the question of internal clocks. You don't have just one. Your body hosts a complex network of biological timers, some centralized, others distributed. The central pacemaker is the suprachiasmatic nucleus, SCN, located in the hypothalamus. It regulates circadian rhythms, roughly 24-hour cycles tied to light and darkness. But beyond that, there are peripheral clocks in your liver, your skin, your lungs, that coordinate with the SCN, but also operate semi-independently. This distributed system synchronizes countless functions: hormone release, body temperature, alertness, digestion. It's not just about when you sleep or wake. It governs when your blood pressure rises, when your cognitive performance peaks, when your immune system responds most effectively. Chronobiology, the study of these rhythms, has revealed a layered architecture of time inside the body. There are ultradian rhythms, shorter than a day, circadian rhythms, about a day, and infradian rhythms, longer than a day, each with their own cycle, each influencing different aspects of physiology and behavior. And while we often think of these rhythms as internal, they are exquisitely sensitive to the external world. Light is the master regulator. Photoreceptors in the eye, specifically in a small subset of retinal ganglion cells, detect ambient light and send signals directly to the SCN. This synchronizes your internal clock to the day-night cycle. Even small exposures, say 10 lux of light at night, can shift your phase. In evolutionary terms, this tight coupling to the sun ensured alignment with environmental conditions. But modern life breaks that alignment. Artificial light, irregular schedules, digital screens, they all confuse the system. The result is circadian disruption, misaligned clocks, poor metabolic regulation, impaired cognitive performance. Jet lag is the extreme version. But even small shifts, like daylight savings time, can measurably increase heart attacks and workplace accidents. Time, it turns out, has a preferred shape inside you. And when you distort that shape, the system responds with friction. This is why timing matters, not just what you do, but when you do it. Your body has a chronotype, a biological preference for early or late activity. It's partly genetic. Morning types peak in alertness earlier in the day, evening types later. Ignoring this, forcing early wake-ups for a natural night owl or late shifts for a morning lark, leads to measurable declines in performance and health. The mismatch between internal time and external demand is called social jet lag, and it has consequences: higher rates of obesity, depression, substance use. It's not about laziness or willpower, it's about synchronization. In other words, the problem is not that your life is too short, it's that your time is misaligned. And there's another layer: subjective time versus objective time. Clocks give you one answer, your body gives you another, your perception gives you a third. So, which one is real? All of them. Time is not a single thing. It is a convergence of systems, physical, biological, cognitive, emotional, all interfacing with the same illusion: that something is moving forward, but nothing moves. In the equations of physics, time does not pass. The future and past exist in the same framework. Einstein's relativity shows that simultaneity is relative. What happens now to you may happen later to someone moving at a different velocity. There is no universal moment, only local ones. This is called the block universe theory. It suggests that time is a dimension, like space. The past, present, and future all exist, but you only experience one slice at a time. In this view, consciousness is like a spotlight, illuminating one frame after another, creating the illusion of movement. But the frames themselves don't change. You do. Whether or not this model is true, it reveals something important. Your experience of time is inseparable from your position in it. So, where does that leave you? With a strange kind of agency, you cannot stop time, but you can influence its shape. You can tune your perception. You can rewire your memory. You can realign your rhythms. You can compress or expand your subjective experience. Time is not neutral. It is participatory. And if there is meaning in time, it lies not in its passing, but in how you move through it, not mechanically, but consciously. Space-time's fabric. In the next section, we'll begin looking outward, beyond the brain, beyond the body. We'll explore what time looks like under Einstein's lens, how it bends under gravity, slows near light, and warps in the presence of mass. Because out there, in the cosmos, time behaves even stranger than it does in your head. But that's for later. This is where the groundwork ends, and where the distortion begins. Time, in Newton's world, was absolute, a constant backdrop against which all motion occurred. Like a canvas stretched taut, time existed independently of anything that happened within it. Whether a planet moved or stood still, whether a person aged or didn't, time continued at the same pace, everywhere, for everyone. This was more than just a convenient assumption. It was foundational to how classical physics operated. Without absolute time, how could velocity, force, or acceleration be consistently measured? It was the axis against which all physical change was mapped. But Newton's canvas cracked in the early 20th century. In 1905, Albert Einstein published a paper titled "On the Electrodynamics of Moving Bodies." Within it, a subtle but devastating idea. Time is not the same for everyone. It is not a universal river flowing through the universe. It is something local, something elastic. This idea came to be known as special relativity. At its heart was the recognition that the speed of light is constant. No matter how fast you are moving, if you shine a light, you will measure its speed as the same: 299,792,458 meters per second. That constancy breaks Newton's assumption. If light speed is fixed, then time and space must flex to preserve it. From this emerged two conclusions: time dilation and length contraction. If you move faster relative to someone else, your time slows down. Your clocks tick more slowly. Not just metaphorically, literally. Two synchronized watches, one left on Earth, one taken on a high-speed rocket and returned, will not match when reunited. The one in motion will have experienced less time. This has been confirmed experimentally many times. Muons, unstable particles created in Earth's upper atmosphere, should decay before reaching the ground. But many don't. Their decay is delayed because, from their perspective, time is passing more slowly due to their speed. The phenomenon is not limited to particles. It applies to anything moving close to the speed of light. The faster you go, the slower your internal clock ticks compared to an observer at rest. This is not an illusion. It is built into the structure of space-time itself. Space and time are not separate entities. They form a single four-dimensional fabric, space-time. An event in the universe is not defined by where it happens or when it happens, but by both simultaneously. Change the speed, change the frame of reference, and you change what counts as simultaneous. This leads to the loss of an absolute now. What is happening now to you may already be the past or the future to someone else, depending on their motion relative to you. In relativity, simultaneity is relative. There is no shared present moment. The idea of a single universal now is a convenience that fails under high-speed observation. This reshapes causality. Events are constrained not by absolute time, but by the structure of space-time. The speed of light acts as a causal boundary. Nothing, not information, not influence, can travel faster. It defines what events can affect each other. This boundary is known as the light cone. Imagine an event, a flash of light in the darkness. From that point, the light expands outward in all directions. Anything within that expanding sphere can be influenced by the flash. Anything outside it cannot. That expanding sphere defines the future light cone. The past light cone contains everything that could have influenced the event. Everything else lies outside, causally disconnected. Not before, not after, just elsewhere. Einstein extended this framework in 1915 with general relativity. While special relativity described time differences due to motion, general relativity introduced another source of distortion: gravity. Gravity, in this view, is not a force but a curvature of space-time caused by mass. The greater the mass, the deeper the curvature. Objects follow the contours of this curvature, not because they are pulled, but because the shape of space tells them how to move. And time bends too. In a gravitational field, clocks tick more slowly. This is gravitational time dilation. The stronger the gravity, the slower the time. This is not theoretical. We measure this daily. GPS satellites orbit Earth at high altitudes, where gravity is weaker. Their internal clocks tick slightly faster than those on the ground. To maintain accuracy, their systems must compensate for this difference. Without that correction, GPS navigation would be off by kilometers within minutes. The effect increases near massive objects. Around a black hole, it becomes extreme. A black hole is the endpoint of gravitational collapse. Matter so dense that not even light can escape its event horizon. The boundary beyond which nothing returns. Near this boundary, time slows dramatically. To an outside observer, an object falling into a black hole appears to freeze, its movement stretched infinitely. From the object's own perspective, it crosses the boundary in finite time. Time, as seen from different vantage points, behaves in utterly incompatible ways, and both are correct within their own frames. This reveals something profound. Time is not a universal river. It is a local condition, a rate at which events occur, relative to the geometry of space-time around them. This destroys the illusion of uniform flow. There is no single clock governing the universe. There are only local intervals, patches of time, ticking at rates determined by motion and gravity. This introduces a new problem. If time is so malleable, what prevents contradictions? What stops the rearrangement of cause and effect? The answer lies in the structure of space-time itself. The speed of light forms the boundary of causality. Events cannot influence each other if they fall outside one another's light cones. This maintains order, even if the perception of time varies wildly between observers. And yet, even within this constraint, the strangeness grows. The twin paradox illustrates this. One twin stays on Earth, the other boards a spacecraft, accelerates to near light speed, and returns. Upon reunion, the traveling twin is younger. This is not a paradox in the logical sense. It's a result of asymmetric motion. The traveling twin experiences acceleration, changes in inertial frames, and different gravitational fields. Time, for that twin, simply passes more slowly. Aging is reduced. The body is younger because less biological time has elapsed. This has philosophical implications. If aging, experience, and memory are functions of time, and time is not fixed, then identity itself becomes frame-dependent. You are not just a location in space, but a trajectory through time, shaped by velocity and curvature. That leads to the question of entropy. In physics, the equations governing the fundamental forces are mostly time-symmetric. They work the same, whether time runs forward or backward, but entropy does not. The second law of thermodynamics states that entropy, the measure of disorder, increases over time in an isolated system. This gives time an arrow. Why does time move forward? Not because the equations demand it, but because entropy does. This is deeply connected to the nature of initial conditions. The early universe began in an extremely low entropy state. Why it did remains unknown. But that improbability sets the direction. From order to disorder, from simplicity to complexity, from past to future. Entropy is not a force, it's a statistical tendency. Systems naturally evolve toward more probable configurations. A broken glass has more possible arrangements than an intact one, so it's far more likely. That likelihood governs the direction of time. And yet, at the quantum level, time becomes even more ambiguous. Quantum mechanics allows particles to exist in superpositions, not in one state or another, but in multiple states simultaneously. When measured, the system collapses into one outcome. But before that, the state evolves according to a wave function, governed by the Schrödinger equation. This equation is also time reversible. There's no preferred direction. So, where does the arrow come from? Some interpretations suggest that measurement itself, observation, interaction, introduces irreversibility. Others suggest that entanglement with the environment, known as decoherence, creates the appearance of collapse, pushing systems toward classical outcomes and giving rise to apparent directionality. Still others propose that time is not fundamental at all, that it emerges from correlations between quantum systems. In this view, time is not something the universe has. It's something the universe does, a relation between changing states, a bookkeeping of transitions. This aligns with certain theories in quantum gravity, where space-time is not continuous but granular, composed of discrete units. At this scale, time may be emergent, not a background parameter, but a statistical property of large systems. In all these frameworks, time loses its intuitive form. It is not a container, not a medium. It is a parameter, a symmetry, a projection. Something born of interaction, not something that pre-exists it. The implications are unsettling. If time is not fundamental, then neither is change. The sense of passage may be a cognitive artifact, a way for observers embedded in physical processes to organize their experiences. And yet, you continue to experience it, moment by moment, not as theory, but as sequence. The theory may undermine the flow, but the brain insists on it, and so the experience continues, not because it is required, but because it is constructed. Deep time. Time in the human mind is measured in hours and days. In the cosmos, it is measured in millions of years. To truly understand time, you must be willing to abandon the scales your brain was designed to use. You must shift from the clock to the strata, from moments to epochs. Consider Earth. It has existed for 4.54 billion years. That number is so large, it resists imagination. But break it down. 4,540,000,000 years. You are alive during a span that occupies not even a full decimal place in that figure. Your entire civilization, writing, cities, agriculture, emerged in the last 0.0000004% of Earth's history, less than the blink of an eye in geologic time. To see time on this scale, you look not to history books, but to stone. The rocks beneath your feet are layers of time. Each layer tells a story of volcanoes, oceans, forests, deserts. The science of stratigraphy reads these layers like pages in a book. Not a book written linearly, but one built slowly, sediment by sediment, with some pages eroded, others buried, and still others rewritten by heat and pressure. The Grand Canyon exposes 2 billion years of geological history. Stand on its rim, and you're looking into a trench of time. The oldest rocks at the bottom are Vishnu schist, formed in an ancient seabed long before the rise of multicellular life. Above them, horizontal layers of sandstone and limestone, marking ancient deserts, inland seas, and the slow drift of continents. Each line in those rocks is a timestamp, not in hours or minutes, but in the language of isotope ratios and fossilized coral reefs. Even deeper than rock is the language of isotopes. Radiometric dating uses the decay of unstable elements, uranium, potassium, carbon, to measure time. These clocks don't tick in seconds. They tick in half-lives, spans over which half of the atoms in a sample decay into daughter elements. Carbon-14 has a half-life of 5,730 years. Useful for dating organic materials up to about 50,000 years old. For older samples, scientists use uranium lead dating, with half-lives in the hundreds of millions of years. These radioactive isotopes are natural clocks embedded in matter. The same physics that defines time in Einstein's equations also allows you to reconstruct time in Earth's deep past. The Earth itself is a system of rhythms. Plate tectonics move continents over tens of millions of years. The planet has reorganized itself many times. Pangaea, Gondwana, Laurasia, each configuration shaped climate, biodiversity, and extinction. Time shapes life, but life also shapes time. The Earth's atmosphere, once oxygen-free, was transformed by microbial life, specifically cyanobacteria. Around 2.4 billion years ago, photosynthesis began releasing oxygen into the oceans and air. This event, called the Great Oxidation Event, fundamentally altered Earth's chemistry. It also introduced a new kind of time, evolutionary time. Evolution is not a directed process. It is a statistical accumulation of changes in genetic material filtered by environmental pressure. But over long enough periods, randomness becomes structure. Consider the Cambrian explosion 541 million years ago. A sudden diversification of animal life, complex bodies, shells, sensory organs, emerged in a relatively short geologic window. In evolutionary terms, short still means 20 million years. But compared to the preceding billion years of microbial simplicity, it was rapid, and it left records, trilobites, brachiopods, early arthropods. These fossils are not snapshots. They are sequences, evidence of transition, indicators of an arrow of complexity drawn across biological time. But complexity is not guaranteed to rise. Mass extinctions reset the clock. There have been 5 major extinction events. The worst was the Permian-Triassic extinction, 252 million years ago. It wiped out 96% of marine species and 70% of terrestrial vertebrates. The biosphere nearly collapsed. It took millions of years for diversity to recover. From that void, new evolutionary pathways emerged, dinosaurs among them. Extinctions restructure evolutionary time. They compress it, erase long-established lineages, reset ecological dynamics. Then there is the Cretaceous-Paleogene extinction, 66 million years ago. A sudden event, an asteroid impact near present-day Yucatan, ending the age of dinosaurs. From that chaos emerged mammals, not as conquerors, but as survivors. Small, adaptive, nocturnal. Over time, they diversified. Some walked upright, some formed language, some built calendars. The progression of life is not a march, it is a branching, a constant divergence and pruning. And human time, measured in days, in generations, is a thin filament growing from this complex braid of evolutionary time. You measure history by human artifacts, but deep time holds patterns far older. The Milankovitch cycles. These are slow changes in Earth's orbit and tilt, eccentricity, axial tilt, and precession that occur over tens of thousands to hundreds of thousands of years. They modulate solar energy reaching the Earth, influencing glacial and interglacial periods. The last ice age ended around 11,700 years ago. The Holocene began. This is the epoch in which agriculture arose, cities formed, and written language emerged. You live in a warm interval, a brief stability, but the planet's cycles are not paused. They continue. The Earth's axial tilt shifts slowly. Its orbit varies. These rhythms, imperceptible in human time, dominate in planetary time. Time exists in cycles, not just lines. You can see this in tree rings, in ice cores, in sediment layers. Each layer encodes a moment, not a date, but a condition. Temperature, atmospheric composition, pollen count. From these proxies you reconstruct time, not as ticking, but as transformation. Ice cores drilled from Greenland and Antarctica contain bubbles of ancient atmosphere. Trapped within them, past concentrations of carbon dioxide, methane, oxygen isotopes. From these, scientists mapped climate patterns going back 800,000 years. This is a record not of time itself, but of what time did, and what it undid. Civilizations, too, follow temporal arcs. They rise, stabilize, fracture, collapse, often following ecological or climatic pressures. The Sumerians irrigated the Tigris and Euphrates. The Mayans tracked celestial movements with extraordinary precision. The Egyptians built solar calendars from the flooding of the Nile. Timekeeping and environmental observation are inseparable in early civilizations. But these observations were local, Earth-based. It was only with astronomy that humans began to understand time on a universal scale. The calendar is not arbitrary. It is a projection of celestial mechanics. The year is Earth's orbit. The day is its rotation. The month is loosely tied to the moon's phases. The week has no celestial anchor. It is cultural, a human rhythm imposed upon natural cycles. Timekeeping evolved from observational astronomy. The Babylonians divided the sky into degrees. The Egyptians built sundials. The Greeks built mechanical models of planetary motion. The Antikythera mechanism, an ancient Greek analog computer, modeled lunar and solar cycles, including eclipses. Mechanical timekeeping emerged from these origins. In medieval Europe, the first weight-driven clocks were installed in monasteries to regulate prayer. They ticked in hours and bells, not seconds. Precision increased with pendulums, then springs, then quartz, and finally atomic clocks. Each advance reduced the scale of measured time. The cesium atomic clock defines the second as 9,192,631,770 oscillations of the microwave radiation, corresponding to a transition in cesium-133 atoms. Time has been reduced to a quantum resonance, and yet The purpose of these measurements remains rooted in something ancient: synchrony, coordination, prediction. Even now, Earth's rotation is not perfectly regular. It slows by milliseconds per century due to tidal friction with the moon. Leap seconds are occasionally added to coordinated universal time to account for this irregularity. Time, at every scale, remains unstable. In geology, time records transformation. In biology, it marks variation and selection. In astronomy, it defines orbital resonance and stellar lifespans. In technology, it becomes ever finer, yet never fixed. The more precisely you measure it, the more you recognize that time is not one thing. It is layered, nested, contingent. It is change made legible, and your position in it is always temporary. The end of time. You can look backward into time. Fossils, radiation, memory. They all carry impressions of the past. You can also observe the present, imperfectly, with instruments and thought. But the future, there is no data from the future, and yet physics describes it, not with certainty, but with projection, not with images, but with curves. To speak about the future of time, you must set aside intuition. Intuition was shaped for survival, seconds, minutes, perhaps years. It was never meant to handle billions of years, or the cooling of galaxies. But physics has no such limitations. Begin with the stars. The stars you see now are in midlife. Hydrogen fuses into helium in their cores, releasing energy. This fusion pushes outward, balancing the inward pull of gravity. As long as this balance holds, the star shines. But fuel is finite. In about 5 billion years, our sun will exhaust the hydrogen in its core. It will swell into a red giant, expand beyond the orbit of Earth, then shed its outer layers, leaving behind a white dwarf, dense, hot, but no longer fusing. That white dwarf will slowly cool over trillions of years, fading into a black dwarf, cold, dark, inert. Multiply this fate by the hundreds of billions of stars in the galaxy. That's stellar time. Now scale out. Galaxies move. They are not static pinwheels. They drift, pulled by the mutual gravity of their mass and the invisible scaffolding of dark matter. Galaxies merge. The Milky Way and the Andromeda Galaxy are on a collision course. In about 4 billion years, they will begin to merge, forming a new structure, perhaps an elliptical galaxy. Stars will pass mostly unharmed through vast empty space, but the shape of the sky will change. Constellations will dissolve. Still further into time, galaxy clusters continue merging, but space itself is expanding. Not like an explosion, but like a stretching fabric. This expansion was discovered in the 20th century, when astronomers observed redshifted light from distant galaxies. The farther the galaxy, the faster it recedes. This is not motion through space. It is space itself growing. And the rate of expansion is not slowing, it is accelerating, driven by something unknown, dark energy. Dark energy is not well understood. It is not matter, not radiation, not anything you can hold or see. But it has a property: negative pressure. It causes space-time to stretch faster and faster. Over billions of years, this leads to a phenomenon called the cosmic event horizon. Eventually, galaxies beyond a certain distance will recede faster than the speed of light, not because they are moving fast, but because space is stretching between us and them. Beyond that horizon, no signal can ever reach us, not even light. The visible universe will shrink, not in size, but in content. Fewer galaxies, less structure, more darkness. In 100 billion years, the only galaxy we'll observe may be our own. Then comes the slow death. Stars, having exhausted their hydrogen, become white dwarfs, neutron stars, or black holes. Fusion ceases, light fades, stellar remnants drift. After trillions of years, star formation stops. No new light, the sky darkens. This is the degenerate era, It will last longer than everything that came before it. Black dwarfs made of degenerate matter will persist. They may collide occasionally, sparking rare explosions, but overall, the universe will be quiet, cold, sparse. Still, entropy continues. Black holes remain, they do not shine, but they influence everything near them. They consume mass, bend time, distort space-time, and eventually, they evaporate. Stephen Hawking showed that black holes emit radiation, Hawking radiation, due to quantum effects near the event horizon. This radiation causes the black hole to lose mass. It is unimaginably slow. A black hole the mass of the Sun would take 1,067 years to evaporate. Larger ones, longer. As they shrink, they emit more radiation, ending in a final flash. Then, nothing. After the black holes evaporate, only subatomic particles remain. This is the dark era. No stars, no black holes. Just a near absolute zero universe filled with particles and low-energy photons, expanding into silence. Protons may decay. Current physics does not require it, but some theories suggest they do, over time scales of 10 to the 34 years or longer. If true, even the last atoms will disintegrate. If not, they will drift forever. In either case, entropy increases, energy spreads, structure dissolves. Eventually, the universe reaches thermal equilibrium. The same temperature everywhere, no gradients, no movement, no change. This is the heat death. Time, in thermodynamic terms, requires gradients. Differences in energy drive processes. But in heat death, there are no differences, no usable energy, no possibility of work. It is not an event, but a condition, an asymptote. This is where the second law of thermodynamics leads, not because anything is broken, but because the probability of high-order systems spontaneously forming is infinitesimal. The arrow of time points forward because disorder is more likely. And when maximum disorder is reached, time becomes meaningless. Not because clocks stop, but because there is no longer anything to distinguish one moment from the next. There are alternative scenarios. If dark energy is not constant but increases, it may trigger a big rip, a future where expansion accelerates to the point that galaxies, stars, planets, and even atoms are torn apart. Alternatively, the expansion might reverse if dark energy is transient. This would lead to a big crunch, a collapse of all matter into a single point. Some models propose a big bounce, a cyclic universe, expanding and collapsing indefinitely. But the best supported model, based on current observation, is heat death. It does not feel dramatic. It is not an explosion or a collapse. It is the end of structure, a soft erasure. This timeline dwarfs all others. The entire history of human civilization, from cave paintings to space travel, has occurred in the final flash of stellar abundance. You exist in a thin interval of high entropy production, low disorder, and rich structure. The universe is tuned for complexity now. It will not be forever. Your experience of time is tied to this abundance. Stars shine, matter clumps. Entropy has room to increase. That is why thought occurs, and memory, and direction. But in the far future, time becomes less about what happens, and more about what doesn't. No change, no clocks, no systems to evolve, just infinite expansion and empty stability. This challenges the assumption that time always has meaning. Without observers, without change, without structure, does time persist? Physics says yes. Entropy still increases, quantum fields still fluctuate, but meaning, the idea that one moment leads to another, becomes a human projection. In a heat-dead universe, duration is irrelevant. The clock ticks, but there is no one to hear it. This is not pessimism, it is scale, and that scale is inescapable. Time, as understood by cosmology, is not a cradle for humanity. It is a window we happen to occupy, brief, fragile, unlikely. The laws that govern this future are already visible. You measure them in supernova-like curves, in background radiation, in redshifts and decay chains. They are not hidden, and they do not care. In this, time becomes not a story, but a boundary, a framework that marks the beginning of structure and its final dissolution. It is not cyclical. It does not return. It simply extends until extension no longer has meaning. The story of time. You are a conscious interval, a locus of perspective, a bridge between past and future. Time is not your enemy, nor your possession. It is your condition. It is the framework that makes meaning possible. And within that framework, you choose how to live, not forever, but fully.